Good morning, everybody. This would usually be the place where I introduce myself, but Tomasz just did a much better job of it than I could ever have done. So thank you for that, Tomasz. And that allows you to dive in straight into the actual interesting part of the talk, which is recursion schemes. Now, I want to talk to you about recursion schemes, not necessarily so that you learn about them, although you will, hopefully, but this is more of a revenge story, really, because, well, you all have had that experience, or you will have it soon. When you're learning functional programming, it's all a bit overwhelming at first, isn't it? You have to learn so many new complicated things, unlearn so many other complicated ones, and it comes at you from all directions, and it really feels like you're never going to get it. But then at some point, something clicks, and you actually do understand things, and you realize you know not everything, certainly, but enough that you can start writing code that you're not ashamed of, enough that you can start submitting pull requests to open source projects, enough that you can use functional programming in your day-to-day work and not be terrified of the code review. And this moment is pure bliss. It's an epiphany. You feel one with the universe. It's just an amazing feeling. And that, of course, for me lasted about 30 seconds. Because a friend of mine called me and said, Nicholas, do you know about recursion schemes? To which I had to confess, I didn't even understand all the words in that sentence. So back to the books I went, watched a lot of talks from very gifted speakers, read a lot of blog posts, papers, articles, and I came to the following conclusion. Recursion schemes are a bit rubbish. They sound extremely pretentious. They are very complicated to put together, and the benefit is at best dubious, because the usual sales pitch goes something like, if you have to write a simple mathematical programming language, then doing it with recursion schemes is almost as good as doing it without. Didn't find that compelling. So I came back to my friend and told him exactly that, what I just told you, to which his answer, which I felt was a bit of a low blow, was, no, but you don't understand, Nicholas. You cannot be a proper functional programmer if you don't know recursion schemes. And I dearly want to be a proper functional programmer. So I went back to studying, and this time I came away with a slightly different conclusion. Recursion schemes are not rubbish. The way they are taught, however, definitely is, at least for people like me. You see, recursion schemes are a beautiful theoretical construct. The calculus of recursion schemes is a thing of beauty, but also kind of obscure, and tackling them via the theory only just doesn't work for someone like me who needs to know what's in it for me, to have an intuition about how they're going to be used and why they're going to help me in the future before I can commit that much mental energy to learning something. And so here we are, and I'm giving you the talks that I wish somebody had given me when I first started learning recursion schemes. And my promise to you is, by the end of the talk, you will know what recursion schemes are and what they might be used for. But more importantly, you will have all the tools you need to derive other recursion schemes. We're going to focus on one, maybe two existing ones, but there's a whole lot of them. And I'm going to give you all the tools to be able to understand the other ones, and even to come up with your own recursion schemes should you need to. And of course, by the end of the talk, you too will be a proper functional programmer. So that sounds good to you. Let's get started. And the first step to understanding recursion schemes is understanding recursive data types. You probably already know about recursive functions, functions that are defined in terms of themselves. Recursive data types are very similar in that there are data types defined in terms of themselves. The simplest one I could think of is the linked list, which proper functional programmers call the const list, because that makes a lot less sense, and we like that. And a const list is composed of, can be either a const, which is an empty list, or nil, which is the empty list. And a const is composed of a head, the value inside of the cell, and a tail, which is a reference to the rest of the list. And if the rest of the list happens to be nil, then you've reached the end of your list and you're done. This is fairly straightforward to implement in Scala. You'd have a subtype list, which can either be a const or a nil. And if it's a const, then it contains a head and a tail. And if you look at the type of head, we're not even making a polymorphic list. This list is monomorphic. It only contains integers. Because what we're going to be doing is we're going to generalize that all the way to the most abstract possible representation of it. And I find it's always easier to start from the simplest possible scenario when you generalize, because then you reason about simple things and then you abstract over the complexity. So we're doing the simplest possible list. You can then create values of that linked list, which is not amazing. There's a bit of noise, but if you squint, you can see your list 3, 2, 1. Creating values of recursive data types is a common problem. It gets noisy really quickly, but there are solutions to that problem. Right, now that we know about recursive data types defined in terms of themselves, how do we work with them? Instinctively, you'd think, well, it's a recursive data type, right? So I'm going to need recursive algorithms. And of course, given the title of the talk, this is where we're headed. And the most important, the most common recursive algorithm that you use to work with recursive data types is called natural recursion or structural recursion. It's a pattern in which you let the structure of your data type guide the recursion. So for example, we could compute the product of a list. This would take a list and return the product as an int. And in order to do so, what it does is it pattern matches on the list. Here we have a cons. So we take the head, 3, and multiply it by the product of the tail. We have another cons where the head is 2, which we multiply by the product of the tail. And yet another cons where the head is 1, which we multiply by the product of the tail, which in this case is nil, which we map to 1. That tells us that the product of the list 3 to 1 is 3 times 2 times 1 times 1, which yields 6, which is, of course, exactly what we wanted to have. But if you look at this from a slightly higher perspective, what we've done is provided a solution for the simplest possible problem. The simplest possible list, the smallest possible list, is the empty list. You cannot have a list that's negative size. So this is the smallest possible problem. We map that to 1. And then we tackle compound problems, more complicated problems that are composed of a smaller problem and additional information, the head. And we just rely on the fact that we know the solution to the smaller problem, and then we update that and return a solution. This is a pattern that comes up a lot. We could, for example, compute a string representation of a list. It takes a list, returns a string by pattern matching, and the smallest problem, the empty list, has a solution of the nil string. And more complicated problems will map to the head concatenated to cons, concatenated to the string representation of the tail, so the solution to the smaller problem. And that will, of course, give us the expected result, the 3 cons 2, cons 1, cons nil string. What have we learned? We have learned so far that structural recursion works by providing a solution to the smallest problem. And then for larger compound problems, we rely on the solution to smaller problems and do our work. And if that makes you feel of proof by induction in mathematics, that is, of course, not at all a coincidence. Right. So now, structural recursion appears to be a useful tool. It seems to be a bit of a shame, though, that we have to rewrite everything from scratch every single time, doesn't it? So what we're going to do is we're going to try and generalize it. We're going to generalize structural recursion. In order to do so, what we'll do is we take mkstring and refactor away all of the hard-coded bits. So the first thing we'll do, of course, it's not called mkstring anymore. It's called recurse. Recurse is not a good name. We're going to come up with a better one later. But my reasoning here is we don't yet know what we're going to end up doing. We don't yet know how it's going to be used. Right now is the worst possible time to name that function. So we're going to give it the worst possible name if we actually try to find a good one. So we give it a rubbish one, and we'll update it later when we actually know what it is we're doing. So we have recurse, which, if you think of it from a more visual perspective, looks something like that. Go from a list, use the structure of that list to turn it either into a head and a tail or the empty list. You recurse on that to get a head and a solution to the tail, the string representation of the tail, and then you use some hard-coded magic to get to the string representation. And this is what I want to get rid of, the hard-coded magic. And the first step is going to take care of the base case, the solution to the smallest possible problem, which in terms of code is right here. That's the hard-coded string nil, and it seems very straightforward. We extract that into a constant, and we replace nil by that constant. It's not perfect yet, though, because we had a hard-coded value. Now we have a hard-coded constant. So let's make base into a parameter to recurse. And of course, we must not forget to update the call to recurse. And that still gives us the same result as before. We haven't broken anything yet. And in terms of diagram, we've gotten rid of nil and made it into a parameter, which is nice. We still have to do that horror, though, which is easier than you think, because if you look at it, that's just head and the solution of the tail passed to a function applied to the head and solution to the tail. So let's extract that to a function step, which does exactly the same thing. And this allows us to replace that hard-coded thing to a call to a function step. And of course, we're also going to make step into a parameter and update the call to recurse. And we get exactly the same result, only in a more generic way. And in the diagram, we have replaced that hard-coded bit with step, a parameter, and we still have some hard-coded things, but not at the value level, at the type level. We're still working exclusively with strings, and we know that's not what we want, because we have examples of other algorithms that don't return strings. Product returns an int, for example. We'd like to abstract over the return type. But if you look at the code, that's actually not very hard at all, because even though everything is a string, we don't need it to be a string. We need the parameters to match, but we don't use the fact that the type is string. So when you have this kind of pattern, you can just declare a new type parameter and replace string by that type parameter without actually changing the meaning of your code. And we get the same result. And this is much nicer now because we don't have anything hard-coded anymore. The base case, the state case, and the return type are completely general. Now, I'm happy with that diagram, but I still want to fiddle with the code a bit. I don't like that bit. It's a bit noisy. There's so many parameters, and it's frustrating because we already have base in scope and step in scope. So we could make that better. And in order to make that better, what I like to do, not everybody likes it, but I do, and this is my talk, so we'll do it my way, is I'll take the pattern match and extract it to a helper method, helper function, which is traditionally called loop or go. I'm calling it loop here. And that's exactly the pattern match. And then the body of the function is just an application of that helper function. And in here, we have step in scope, we have base in scope. So the recursive call to loop is much clearer. And I feel that expresses the purpose of the code, the meaning of the code much more clearly, because step is now much more obviously a function that takes a head and the solution of the tail. And of course, this is just internal refactoring. We haven't broken anything. Well, we do have to change the diagram a bit because we're not calling recurse anymore for the recursive part, we're calling loop. Now, this appears to be the final diagram for our function, but I'm still not a big fan of that. Recurse takes a values, this parameter, which is called values, and passes it directly to loop. It doesn't even need to know about parameter. We could return loop instead. Of course, that forces us to update the return type to function from list to A, because loop is a function from list to A, and everything works almost as it did before. It's slightly more complicated because we now have two parameter lists, not just one, which is arguably more complicated. So it might not seem like a great idea to do what I've just done, but the reason is we're going to use recurse mostly to create combinators. We're not going to call it directly. Take mkstring, for example. You could express it that way. But I argue that if you get rid of the int parameter and change the return type to a function from list to string, then of course you can make mkstring into a value. Then it's much more obvious what mkstring is. It's a specific kind of recurse applied to that base in step. It's not with ints all over the place. So I find that's clearer. It's more easy to understand what mkstring is. Right. So now I'm happy with our recurse. We have to name it. This is something that functional programmers, the proper ones, really enjoy doing. And very often we come up with obscure names, but in that specific case, I kind of like what we came up with. Because recurse, what it does is it takes a list and gently folds it on itself until we get a single value. This is why it's called fold. And I find that to be a very poetic name. So this is fold. And we've just seen that fold works just fine for mkstring because that's what we've been doing all along. But can we express other structural recursive algorithms using fold? Well, certainly, product, for example, is a fold where the base step is 1, and the step case is the product of the head with the product of the tail, the multiplication of the head with the product of the tail. What have we, of course, that yields the expected result. What have we learned here? Well, we've learned that we could generalize structural recursion by parameterizing the base case, parameterizing the step case, but also, unfortunately, knowing the structure of our type, because this only works for list. It seems like a bit of a shame though, doesn't it? It would be so much nicer if we could apply that to a lot more types. And this is what we're going to try to do. We're going to try to generalize folds, or if we unfold that, generalized structural recursion. It starts getting recursive in the definition itself. And in order to do that, we're going to use exactly the same technique. We're going to take fold, and we're going to refactor it until we're happy with it. Now, look at that diagram. The diagram for fold that we came up with before. If you look at that bit, where we hard-code the structure of the list, because we split the list in a cons or a nil. So that's definitely the structure of the list. But another way to look at it is list is either a head and a tail, or it's nothing. It's maybe a head and a tail. It is exactly an optional head and tail, and we have a data type for that in Scala. We have option. A list could be thought of as an option of head and tail. Let's try to do that. Here we have our hard-coded structure, and we want to get rid of that. But in order to be able to get rid of that, we need a function that will project our list into an optional head and tail. This is fairly straightforward, because if we have a cons, then we have a head and tail, so we map that to a sum of head and tail. And if we have a nil, we do not have a head and tail, so that maps to null. Right, that allows us to not work with a state as a list, but to project the state into an optional head and tail. And of course, cons of head and tail now becomes sum of head and tail, and nil becomes null. And well, we need to get the projection as a parameter to a function. Great, everything works. In terms of diagram, we've turned that into the admittedly slightly more complicated diagram. And warning, the diagram is going to get worse before it gets better. But it will get better, so just bear with me. It might look like we're headed straight into a wall, but we're actually going to get somewhere. Right, we've introduced a new type here, option of head and tail. And when we do that while working on an algorithm, it's usually a very good idea to look at the overall algorithm and see whether that type doesn't appear anywhere else, so that you can reuse it. And that way, you might find a common pattern, maybe something you can extract over. So does option of head and tail appear anywhere else in that diagram? Well, in a way, if you kind of squint, it does here, because step is a function from a head and a tail to an A, and base, in a way, is a function from nothing to an A. So clearly, step and base look like the two branches of a single function that goes from an optional head and tail to an A. We can make that more concrete. We can try and merge base and step. In a function that I'll call op, because I'm really bad at naming things, and we'll have a much better name for that later. And op is simply a matter of, if we do have a head and tail, then we call the step case. And in the case of MK string, we know that the step case is a concatenation of head with cons with the result of the tail. And we know that none maps to the base case, which in the case of MK string is a string nil. Here's up. We can now update fold to not take a base and step, but simply take a node. And of course, thing gets slightly different in the pattern match, because step now is actually up of something, so up of some, and base is up of nothing, so up of none. And the diagram, everything still works, and the diagram, well, gets a bit disappointing, really, doesn't it? Because we have two arrows marked up coming from the same place. This looks, I'm not happy with that, but luckily we can realize that up is applied to both of the output of all the branches of a pattern match, which allows us to take it out of the pattern match and apply it to the result of the pattern match, which allows us to rewrite the diagram to this. Again, more complicated, but now there appears to be something of a pattern here. And we have introduced that new type, option of head and tail. And I want to talk about that a little bit, because I've been calling it option of head and tail for a while now, but it's not really an option of head and tail, is it? I mean, on the left-hand side, this option of int list is very literally an optional head and tail. It's a list that you have projected into an option of head and tail. But on the right-hand side, option of int A is not the tail of the list. It's the solution of the problem we're trying to solve for the tail of the list. And that is a very interesting observation, because this type, option of head something, allows us to have very concrete representation of different steps of the structural recursive algorithm. Option of head tail is the list itself, represented as the recursive part, the tail, so the smaller problem, plus additional information. An option of int A is the next step, where we have an optional additional information, the head, int, plus the solution to the problem. So we have the concrete representation of the fact that we are relying on a solution to the smaller problem to exist. Such an interesting type, actually, such an important type. We're going to give it a name. We're going to call it listf, which is listf is really an option of head and A. And that name listf is not very pleasant, is it? I don't like when we come up with this blah blah f or blah blah a or blah blah r. We do that a lot in functional programming. I'm not a big fan of it, but in this case, well, you probably understand where the list is coming from, right? This is a representation of list, so we'll just take list and stick that in the name because that's easy. And the f part, I'm not going to explain right now. We'll explain in a few slides, not because it's a big secret, but it will be, I hope, a surprise, a nice surprise later. It's not going to be a great surprise. I didn't bring a cake. It's just something fun for people to realize a bit later, so I don't want to spoil it for you. And we use that listf of A type in two places at the moment. We use it when we project a list into listf. And in that case, A is a list. So when we project a list, we take the list and we map the A parameter to the type of the recursive part of the list, its tail, so list. And in the case of op, the type parameter is string, because we're not working with a list anymore. We're working with a solution of the problem to the list. Of course, now that we have defined listf, we're going to use it everywhere in the place option by listf, which allows us to simplify the diagram just a little bit. Not great yet, but it's slightly simpler. But now, this is where it gets slightly creative and intuitive. Look at that pattern. It's a mess of code, it's a mess of a diagram. It's hard to really see what's going on, but in a way, you go from a listf of list to a listf of A by applying this mess, which is basically just the loop function, and that happens to be a function from F to A. Some of you might start thinking, I've seen that pattern somewhere. But let's make it a lot clearer. Look at that pattern match. When we have a sum of head and tail, we return a sum of a function applied to head and tail. And when we have a none, we leave it alone and just return none. This is something that you have seen before. Let's make it even clearer. Let's do the same trick. Let's extract this pattern match into its own function, which I'm going to call go now because loop is already taken, and replace the entire pattern match by equal to go. Look at the pattern match. We go from listf of list to listf of A by applying loop, which is basically a list to A. Even more obvious, let's take loop out of the equation. Let's add a new parameter to go, a function from list to A. So we don't even need loop anymore, we just have a function from list to A. And of course, we must update the call to go. But now, go is a function that takes a listf of list and a function from list to A and returns a listf of A. And that is map. You have seen map, you must have. When you have an option of A and a function from A to B, then you can use map to turn that into an option of B. If you have a list of A and a function from A to B, you get the list of B. If you have a future of A and a function from A to B, then you get a function future of B, etc., etc., etc. It's all over the place. It's an extremely common pattern. It is such a common pattern, actually, that we have a name for it. It's not a very friendly name, but we call that a functor. Technically, we'd call that a covariant functor, but really, everybody calls it a functor. And that name, which sounds very complicated, really just means one thing. It means a type that has a map function that is somewhat sane. That somewhat sane bit is not very interesting. We can tackle that later if you want, but it's not at all useful for this talk. So basically, a function means something that has a map function. When you start saying patterns like that in an algorithm you're trying to generalize, you're on the right track. Because if we can now express listf in terms of that functor thing, we might be able to get rid of it altogether and just say, well, I want a functor. So let's try to do that. Let's see whether we can represent functors in a way that's useful. There are many ways we could present functors, and I toyed for a long time with the idea of using subtyping to do it, because that would definitely work. But proper functional programmers somehow cringe at the idea of using subtyping. Apparently, it makes us non-functional programmers, so we don't actually like to do that. And I would like to leave this talk with whatever's left of my reputation intact. So I'm going to do it the old-fashioned, boring way. I'm going to use type classes. Here's functor, which takes a type parameter, f. F itself must have a type parameter because, well, we need something to map over, right? So if we have an option of A, we map it to an option of B. So this type parameter is the A in option of A. And functor declares a map function that, given an f of A and a function from A to B, here's an f of B. So that's all the functor is. But now that we have defined that, and we know that we want to call map on listf, then we want to say that listf is a functor itself. So we'll do it that way. We'll create a new functor of listf. That's called an instance of the type class. And declare a map function that is basically a copy and paste for the pattern match from before. In the case of sum, so if we have a head and a tail, then we apply f to the tail. Otherwise, we leave none alone. And now, just a bit of boilerplate so that we don't have to make the remaining slides slightly easier. Declare a map function, which is just a helper, given an f of a, function from A to B, and a functor, then it puts everything together so that we don't have to. Given all these tools, we can replace the pattern match inside of Go with a call to map, because that's exactly what it is. So much so, that we can actually not even call Go at all, but call map instead, and get rid of Go, because we don't need it anymore. And that yields exactly the same result as before. In terms of diagram, we've turned that whole mess, which is kind of scary, into a call to a function. And that is beautiful, isn't it? It's at least, you might not agree that it's beautiful, but it certainly is simpler, isn't it? Now, we have simplified things quite a bit, but we still have hard-coded the structure of the list. Listf is very concretely a list. It's an optional head and tail. That is a list. Let's try to get rid of listf. Well, it's not going to be that hard, because if you look at the code, the only thing we need to know about listf is that we can call map on it. So we don't need that to be listf. We need that to be an f that also has a functor instance. Fair enough. Let's do that. I'm working with an f that has a functor instance, and I can replace listf by that. And the code still compiles and runs exactly like before. Great. We don't have listf anymore in our diagram. We just have f. We do still have list, though, the input type itself. That's still hard-coded. But it really does not need to be, because as before, we don't use the fact that list is a list. We just use the fact that we can project into it, that we have a project function that makes sense. We really don't need to know it's a list. We just need to know that we can project into it. So we could declare a new type parameter and replace list by that type parameter without actually breaking anything or changing the meaning of a function. And now, well, this is sort of beautiful, isn't it? We've gone from that very complicated for diagram to something that's fully generic. Right. We have to name it. And, well, this is one of these names. Fold is not called fold when it's generalized. It's called catamorphism, kata for short. Now, that's a scary name. It's a very hostile name. But if you understand where it comes from, it's actually very easy to remember it. Catamorphism is composed of two terms, kata and morphism. Kata means, I know ancient Greek. Morphism means, I know category theory. So catamorphism means, I know more than you do. And when you know that this is what people mean when they say, I know catamorphisms, then it's a lot clearer and simpler to follow. Now, of course, up is not called up, obviously. The name it's got sounds a lot more clever, but it's also the most overloaded term in functional programming. Everything is called an algebra. To the point of obfuscation, everything is an algebra. So when you tell someone, do you have an algebra? I don't know, which kind do you need? But that's called an F algebra. It's called an F algebra, if I want to be pedantic, which of course I do. And well, and we also have defined this F, which has a nice name as well. This F is very important, right? It's a functor that guides the entire recursion. This is how we represented the recursive part of our list and abstracted over it so that we could have either the recursive part of the list or the solution to the recursive part. That's the magic of recursion schemes. That's everything you need to know really about recursion schemes. It's that thing which is called a pattern functor or a base functor, depending on the papers you read. They mean the same thing. It's very convenient. Two different names to mean exactly the same thing. Another case of brilliant naming, but I'm going to be calling it a pattern functor. And of course, applying kata to all of the stuff that we defined before is exactly the same result. Now, up is not called up, it's called an algebra. And this is the final diagram for catamorphisms. And we've done catamorphisms for MK strings. This is what we've been doing so far. But what about product? Can we do product as a catamorphism? Well, yes, if we define the right algebra, of course. But in the case of product, the algebra is, if we have a head and a solution, the product of the tail, then the product of the entire list is a head multiplied by the product of the tail. And if we don't have a head and a tail, if we reach the end of the list, then the product is 1. Now, product itself is simply an application of kata to the right algebraic projection. And of course, that yields the exact same result as before. Right. What have we learned so far? We've learned that catamorphisms are structural recursion for types that can be projected into pattern functors. List can be projected into a pattern functor, list F. And that's all we needed to be able to do structural recursion on it. Catamorphisms are far less complicated than their names make them out to be. And they're also a simpler refactoring away from the familiar fault. There's one intuitive step that you have to take. The invention of the pattern functor is a realization that the recursive steps are just a call to map. That's the genius of recursion schemes. And once you have that, you have absolutely everything else. And of course, catamorphisms are your first ever recursion scheme. They're a recursive pattern, structural recursion, that we have abstracted and abstracted and abstracted yet again to get to something that has a very recognizable name. Not a good name, but at the very least a very recognizable one. And that tells people that see the code, oh, I know what that is. It's a common pattern. I know exactly what it is. So I don't have to think about what goes on inside. I know what the code means. That is a design pattern. We, of course, are not calling that a design pattern because that sounds like OP, doesn't it? And we don't, us proper functional programmers, don't want to be mistaken for Java programmers. We don't want that. So we're not going to call that design patterns because we don't want to look like we're part of the gang of 4. We're going to call that a recursion schemes because that makes us sound so much smarter. But it's just really a design pattern for recursion. Right, now, I'm telling you structural recursion, that catamorphisms are structural recursion for types that can be projected into pattern functors. And that sounds very nice. It sounds clever, it sounds good. But I've only ever shown you a list, haven't I? So you could take my word for it, but honestly, I wouldn't. So let's do another type. Let's do the next easiest recursive data type I can think of, the binary tree. Binary tree is composed of a node or a leaf, which is the empty tree. And if you have a node, then you have its value, what's inside of the node, a left branch, which is a reference to the left subtree, and a right branch, which is a reference to the right subtree. And if that happens to be a leaf, the empty tree, then you reach the end of that branch. Again, this is fairly straightforward to implement in Scala. I have some type tree, which is either a node or a leaf. And if you have a node, it's composed of a value, left branch, and a right branch. And you can even create values, although it gets worse and worse, doesn't it? The tree is in there, there's just so much noise around it, but the tree is in there. Now, what problem are we going to solve? I want to compute the height of that tree. The height of a tree, of a binary tree, is defined as the longest path from the root of the tree to a node, to a non-leaf node. And in that case, it's clearly free. And what we'll be doing, what we've done so far is we've gone from the most specific to the most generic. And we're going to do exactly the same thing, but flipping it around. We are going to, of course, use catamorphisms to compute the height, and we're going to go for the most generic possible thing, the expression of the catamorphism, and specialize it to a tree. So let's take a look at the diagram. The first thing we need to do is take that B and make it concrete. But that's easy, isn't it? That's the input type. And we know that the height of a tree takes a tree. So B is tree, done. That's the easy part. Now we need to work on F, the pattern function. One way we could do that is we could do the same trick we learned for lists, kind of by mistake, where list F is just an optional head and tail. Here we could have an optional value left branch and right branch, but I don't like working with tuples or triples. It's parentheses everywhere. The excesses suck. _1, _2, it can't make sense of them. So I'm not going to do that. Instead, I'm going to show you a very mechanical way of going from a recursive data type to its pattern function. Step 1, rename tree, add F at the end. Then do the same thing for the branches. Node becomes node F, and leaves becomes leaf F. Step 1 done. That was the easy part. Now, tree F's got to be a functor. It's a pattern functor, so it's got to be a functor, and a functor needs to have a type parameter to map over. So we need to add that type parameter. And if you remember correctly, in the case of list F, that type parameter represented the recursive part of the list. It represented the list, the tail of the list. So that's the recursive part. And we need that to do the same thing for node F. Node F needs to have a type parameter. It needs to be a tree F of A. And that A represents the left and right branches. Leaf F is slightly weirder because leaf F doesn't actually need an A, but it does need to be a tree F of something. And in Scala, and it can be a tree F of anything because it doesn't care what value is inside of it because it doesn't actually contain any value. So it could be a tree F of anything, which in Scala, confusingly, we call nothing. And of course, if we want that to compile, we need to do something clever. We need to say that tree F is covariant on its type parameter. If that made no sense to you, don't worry about it. You can absolutely think of it as a syntactical trick to get that thing to compile, because that is really all that it is. Right, and there's a pattern functor. It's got everything we need. It's got the type parameter. It's a representation of the pattern of the recursive data type we want to work with. Done. So F becomes tree F here because we make it concrete. But now that we have that, we need to be able to project our tree into a tree F. But given the way we've created tree F, that is very straightforward. We create project tree, which maps a node to a node F and a leaf to a leaf F, and done. That's all there is to it. So project is project tree, and now we need to be able to call map on tree F, which in plain English means we need tree F to have a functor instance, which is actually not very hard to write. Declare a functor of tree F, where given a node F, we apply the function to the left and right branches. And given a leaf F, we don't actually do anything. So nothing to change in the diagram. Tree F now has a functor instance, so we're good to go. And finally, after all this groundwork, we do the one thing that is actually interesting in this entire tree thing, is solve the problem, provide the algebra, the algorithm that we wanted to do, the height. And it's slightly disappointing after all this work, because that's actually very easy. The height algebra forces you to deal with two cases. Either we have a node and the height of the left branch and the height of the right branch. And when in that case, then go back to the definition. The height of a tree is the path, the longest path from the root node to the leaf. So we know that we have that for the left branch and right branch. We know that we have one more node because we have a new root, the node in which we are at the moment. So we take the largest of the left and right heights and add one to that. And in the case of a leaf, well, leaf can't be part of the height, so we just return 0. Algebra is now height algebra. And we're done. This is the concretized diagram for the height of a tree. And height itself now is very easy to write because it's just a catamorphism of the right algebra and the right projection. And of course, that gives us 3, which is the answer we were looking for. What we've seen here is catamorphisms were just finding trees. No difficulties there whatsoever. It does involve a lot of busy work. So we had to define our data type, tree. We had to define a pattern functor for that data type, tree f, a projection from one to the other, a functor instance, before we could even start doing the interesting things. And now, on that note, I leave you with a choice. Depending on how much time I have, I can conclude and go straight to questions, and give you a bit of a cliffhanger too, because I told you, well, there's a lot of boilerplate to do. Finished. Or if I have enough time, Tomasz, let me know, I can show you how to reduce that boilerplate. Nothing from Tomasz?
Yes. Yes. So thank you very much. Thank you very much. We still have 2 minutes left, but generally,
2 minutes. Wow.
yes, 2 minutes left. But if you would like to extend a little bit, it's fine. But for the Q&A session, we should go to the special chat.
Okay, because if I want to talk about this reducing the boilerplate section, that's going to be 10 minutes. So we don't have the time for that, right?
10 minutes. Let me check. Yes, we have 10 minutes.
We have 10 minutes.
Let's go. Yeah.
Let me do this bit because it's actually quite interesting.
Yes.
Right. So reducing the boilerplate. I just told you we have to do so much work. And there's a trick to not doing that work. So I want to show you that because it's actually quite beautiful. The intuition we're going to follow is we don't want to write a recursive data type and its pattern functor and the projection and the functor instance. That sounds like a lot of work. But if you think about it in a certain way, listf and list were extremely similar, weren't they? Listf was a concrete representation of a list. Listf of list is a head and a tail. It's a functional head and tail, so that's very much a list. So it might be possible to write list as a specific kind of listf. And if we were to be able to do that, then we only have one type to define. So let's follow that intuition. Let's see where that takes us. Let's try to write list2. List2 is not called list because it's not our list type, but it is a list. So I have list in the name, and I'm adding 2 in the end to differentiate them. It's going to get a better name soon. And list2 has got to be a listf of something, doesn't it? What is that something? Well, a list is a head and a tail, where the tail is a list itself because it's a recursive data type. So the tail of the type list2 would be list2, wouldn't it? Well, yeah, that would be nice, but that's not actually possible. Scala does not allow us to have recursive type aliases. But we have been doing recursive data types for the past half hour or so. So maybe we could do that. Maybe list2 cannot be a listf of list2, but it can have a listf of list2. Maybe we could have this that way. Now that type, whenever I say it always does not hidden, I find it hard to visualize. And when I do that, I take a pen and a paper and I start drawing things to help me understand what I'm looking at. So let's do that here. Let's declare ins2, which is the 3, 2, 1 nil list, represented as a list2. So a list2, that's a wrapper for a value of something of type, of type listf of list2. Listf of list2 is an optional head and tail. And in that case, we do want to have a head and a tail because we need the head to be free. So we have free, sum of free, and something, a tail of type list2. List2 is a wrapper for something of type listf of list2. We do want to have a head and a tail here because we want to. So we get a sum of 2 and a tail of type list2, which is just a wrapper for something of type listf of list2. Again, we do want to have a head here because we need 1. So this is replaced by sum of 1 and a tail of type list2. And in that case here, list2 is again a wrapper for something of type listf of list2. And we want the empty list because we're done now. So that's going to be a none. And well, you can kind of see the list in there, can't you? It's right here, sum of 3 of sum of 2 of sum of 1 of none, and it appears in the diagram. You also have list2, which is added in the middle. But the interesting thing to realize here is that the structure of the list is entirely in the sum and the nonce is not at all in the list2. That's just structures that we have added to allow recursion. So if list2 doesn't actually encode the structure of the list, but just the recursive bit, then maybe we could do other types with exactly the same mechanism. Maybe we could do tree2 as a tree out of tree2. Maybe that's possible. And tree2 and list2 are exactly the same thing. Certainly they don't have the same name, but we can rename things, and they don't take the same pattern functor. But we could abstract over that, couldn't we? We don't need to know anything about listf, aside from the fact that it's a pattern functor. So let's make that into a type constructor. Listf, of course, now becomes f. And list2 has a type parameter, so we need to add the type parameter. That is f. And we have our list2 here, which we're going to name because, of course, since it applies to any recursive data type, it's not a list2. And this got a pretty funky name, but it's one that's actually fun. It's called fix from the fixed point combinator. Now, why is it called that way? It's called that way. To understand that, you have to go into the definition of what a fixed point and a fixed point combinator are. And the fixed point of a function f is x, such that f of x is equal to x. So that's a fixed point of f, and the fixed point combinator of f is a function fix that, given f, returns its fixed point. So fix of f is equal to x. Let's rework that just a little bit. We know that x is equal to f of x, so we could replace that x with f of x. We also know that x is equal to fix of f, so we could replace that x with fix of f. And now, here's the magic. The code and the mathematical equation are saying exactly the same thing. Fix of f mapped to f of fix of f. And this is why fix is called fix, because it is a fixed point combinator expressed as types. Right, so now that we have that, we can express list in terms of the fixed point operator and its pattern functor. Fixed list is fix of listf. You can even create values, although signal to noise ratio is not great. This is a signal, this is a noise. Clearly, that's not optimal, but it could be worse though, couldn't it? We could be doing trees. Of course, we're going to do trees, fixed tree. It's just the fixed point combinator applied to the pattern functor for tree. And you can create values, kinda, it's right there. If you hate yourself, you could do that. I had to do it. I don't wish it on anyone. But that works. And we have been able to express a recursive data type in terms of its pattern functor. What does that give us for kata? Can we rework katamorphisms in such a way that we use the fact that the input type is now a fixed combinator? Well, first we're going to rename it, of course. We're going to call it katafix. And now, in terms of diagram, what we want to do is we want to get rid of b, because we now know that b, the input type, so list, for example, is expressed as the fixed point combinator applied to its pattern functor. That's fix of listf. So get rid of b and replace it with fix of f everywhere. Great. We have done that. It starts getting a bit mystical. F of fix of f right there. I dive my head in every single time, but it works when you have a gap there. But now we need a projection. And there's two ways we get to the projection. The first one, the usual functional programmer's gimmick, is to say, well, there's only one way the type work. There's only one way I can implement it for the type to work. So I'm going to do that. And if we did that, that would work. That would give us the solution almost immediately, or actually immediately. But there's a slight cost though. If we do that, the only justification we have for the fact that it works is my imaginary friend, the compiler, told me it did. And I don't find that helps a lot with understanding. So I'm going to take the long way around so that you understand it. And in order to do that, I'm going to use my usual trick, refactoring. We're going to start from project, the projection of a list into a listf. We name that project fix and refactor our way to something more generic. We know we want to work with fixed list. And we also know that fixed list is an alias for fix of listf. Of course, now that we've done that, pattern match doesn't work anymore. We're not working with a cons, we are working with a fix of sum. We're not working with nil, we're working with a fix of none. Done. If you look at that pattern match, in the sum case, we just take the sum out of the fix and return it. And in none case, we just take the none out of the fix and return it, don't we? So we could get rid of the pattern match entirely and just unwrap the fix, just get the value that's inside of the fix. And that would work. And we don't actually need to hardcode that to this stuff, do we? We could just, well, we need to make project fix into a method so that we can have a type parameter and replace this stuff by the type parameter. And we have the projection of a recursive data type expressed as fixed point on this pattern functor. It's just unwrapping the fix. That allows us to simplify catafix, doesn't it? We don't need projection anymore. We just unwrap the fix. And we don't even need to get project at all. So catafix got slightly easier, didn't it? And now project is just mapping. And now everything is going to fall into place because that map function needs to be applied to the pattern functor. And the pattern functor, by virtue of being a pattern functor, has a functor instance. So we already have that for free. And the algebra goes from the pattern functor to the output type. And we already have all the algebra that we needed. We have already defined them because we're not working with the initial type anymore here, just a pattern functor. So we could, for example, write product fix, takes a fixed list and returns an int by just using the algebra we defined before. No change there. And that works exactly as expected. But that works for other types as well. Height fix is just a fixed tree to an int by using the height algebra that we defined before and applying it to a catafix, and that gives us exactly the answer that we wanted to have. Now, those were the benefits of fix. These are the costs, though. Look at that pattern match. This is how we do it now. This is how we used to have to do it. Not much more complicated, but it must be said that it is slightly worse because we have a little bit more code here, and we need to know a more complicated type. We don't have a list, we have a fix of sum, which is slightly more complicated. But people will tell me, well, you're not being fair here, Nicolas, because the point of catamorphisms is not to do pattern matches anymore. I don't agree with that, but let's pretend that I do. If you want to use a catamorphism in something, surely you want to have a value of that thing, otherwise there's no point, right? Well, this is how we create a value of list. And this is how we used to. And here, it's very clear that creating a value of list is much, much worse than it used to be. And you're going to have to do it quite a bit, because I hope you're going to use the type, right? So this is not nice, which leads me to the following conclusion. Using fix makes the hard case easier. For me, the data type alpha, because instead of writing the type, its pattern functor and its projection, I just have to write fix as a pattern functor. That made my life easier because I don't have to do these things, which I would have had to do exactly once in the entire lifetime of my data type. But it makes the easy case harder for you, the users, because every single time you want to pattern match or create a value, which you're going to do quite a bit of, then your life gets harder. Which makes me think that using fix makes little sense. It's exactly the wrong trade-off to make, isn't it? If I write a library, it's not to push the hard bits onto you, it's to abstract over them so that you don't have to. And unfortunately, all papers, all articles that you'll see that try to explain recursion schemes are going to do so by saying, right, before we can dive in, I need to tell you about fix. It's not necessary, and it's not even a good idea. And at this point, I'm guessing Tomasz is starting to sweat because we're getting to the end of the talk, so I'm going to conclude now. Sorry. If you only remember just the one slide, this slide is the one you must remember. It's the one in which I point out that I kept my promise to you. You know what recursion schemes are? They're design patterns for recursion. We've seen that. You know everything you need to know to invent your own, because now that you know about pattern functors, everything else is refactoring. So find another recursive pattern that you like, say generative recursion. Stick a pattern functor in there, and before you know it, you will have invented anamorphisms. So that's all you need to know about recursion schemes. And you can study them and study all the really wild bits. Now you have these tools. You can study, for example, the fact that they can compose, which is nice, and that recursion schemes can be duals of each other, so exact opposites, but at the same time, be exactly the same thing. So they can be opposites of each other and the same thing, which is really wild, but really fun to find out. And with that, I think I have told you everything I wanted to, and I dub the proper functional programming.